This graph illustrates sound wave frequency change as a product of speed. We will refer back to it as a roadmap for comparing different scenarios. When a source of sound is at rest, its waves behave normally and predictably. This animation shows sound waves coming from a still source at even intervals. Now we'll introduce the Doppler shift equation to explain this phenomenon. The frequency of the sound waves as it appears to the observer is equal to 1 over 1 plus or minus the velocity of the source divided by the speed of sound, all multiplied by the actual frequency of sound waves being produced. The speed of sound, by the way, is 340 meters per second, or about 760 miles per hour. For a source of sound that is at rest, giving it a velocity of 0, the observed frequency of sound waves is simply 1 times the actual frequency. Things become more interesting when a source of sound is moving. Notice how the wavelength on the left decreases, while on the right it increases. This causes a change in pitch for an observer. Here's our graph again showing plus or minus 200 meters per second. Using the same Doppler equation from before, we can calculate the change in frequency for a source moving at 200 meters per second. Going away, the result is 63% of the original, and coming toward, the change is 240% more.
This is how it would look and sound at 200 meters per second. Something more interesting happens when the source is moving faster than the waves. The waves create a cone shape with the source. Here's our graph again at plus or minus 340 meters per second. When the sound is moving away from the observer, you get 50% of the original frequency. When it's moving towards, the frequency is infinite, thus higher than what we can hear. Here's what it looks like at 340 meters per second.